What's up, guys? This is Jahangir from Emporium, and today we're going to be talking about cycloalkanes. So these are going to be those ring structures that you're going to see, and don't worry, it's not as intimidating as you think. So let's start off by, first off, just writing cycloalkanes so we know what we're looking at. So cycloalkanes, and like I said, these are going to be those ring structures. So if you remember from our past videos talking about the nomenclature, the IUPAC nomenclature naming, you already know that propane is going to indicate 3 carbons, butane 4, pentane 5. So that concept still applies, but we put cyclo in front of that. And we create that into a ring, into a structure. So cyclopropane would be a triangle over here. So we have 1 carbon, 2 carbon, 3 carbons, and this is going to be cyclopropane. Same thing for butane. So we're going to have a square over here, 1, 2, 3, 4 carbons. So this is going to be cyclobutane. So cyclobutane. Then, like I'm sure you guessed, cyclopentane is going to be a pentagon now. So we're going to draw out a pentagon over here. I know my drawings aren't the best, still working on that, but this is going to be cyclopentane. So cyclopentane, and cyclohexane is going to be our hexagon. All right, so let's look at these 3 cycloalkanes. And I want you to pause this video and see if you can identify the correct naming for all of these 3 structures. And just remember, it's the exact same thing as our alkanes, but we're just messing around with these cycloalkanes. So over here, we're first starting off with a cyclopentane. We know this is a cyclopentane because there's 5 corners or 5 sides. So now we have to identify which one is the correct way of numbering these carbons. Should we go from this top carbon over here and down? So this would be the first carbon, second carbon, or should we go from 1 to 2 over here? Now, if you guess that we go from 1 over here, this ethyl is our 1, and then the methyl is 2, then you're correct because this goes with our alphabetic naming. E always comes before M, so we need to make sure that this carbon over here is 1 and this carbon over here is our second carbon. So when we do this, this is going to result in 1 ethyl, and this is going to be 2 methyl, cyclopentane. So our first one over here, the first guy over here is 1 ethyl, 2 methyl cyclopentane. This agrees with our naming rules in that we have our first letter over here being in alphabetic order. So ethyl is going to come first. That E in ethyl is going to come before M. And as a bonus, we're actually going in numerical order as well, going from 1 to 2. So let's look at this guy over here, and I want you to identify if we should start from this bromine and then count to the methyl, or from the methyl and count to the bromine. Now, if you said that we start with the bromine, then you're correct because that B in bromine comes before the M in methyl. So we're going to abbreviate it as bromo because when you're looking at those halogens, you have to abbreviate it to fluoro, bromo, and so forth. So this is going to be our first carbon. Second carbon, so this is going to be 1 dash bromo, and then 2 dash methyl. And we know we have 4 sides, so this is going to be a cyclobutane. So this is going to be cyclobutane. So for our second organic molecule, this is going to be 1 bromo, 2 methyl cyclobutane over here. Now, let's look at our third structure over here. And we have 6 sides, so this is going to be a cyclohexane. And I want you guys to identify if we should start from this ethyl over here or from the chlorine. Now, if you guessed that we start from the chlorine, then you're correct because C in chlorine comes before, or C in chloro comes before the E in ethyl. So this is going to be 1, 2, and 3. So that's the correct way of counting our carbons, and this is going to be, and this is actually going to be a longer one, so I'll write it down here. 1 chloro dash 2 methyl dash 3 ethyl, and let me move this around here to add that cyclohexane. Ethyl cyclohexane. So this is the correct naming for our second structure over here. 1-chloro, 2-methyl, 3-ethyl cyclohexane. Man, that is a mouthful to say. You know, honestly, if you really think about it, organic chemistry should count as an arts credit because of the amount of molecules that you draw. I mean, I'd rather have this qualify as an arts credit than taking like some arts that I have to do and go through all the grades, worry about it. It's just a lot of fuss, but that's just one thought that I had, is that there's a lot of drawing in OChem that I never expected. Anyway, let's talk about stereoisomers now. So in our past video, we actually talked about the different isomers, but just as a review, our stereoisomers are going to be isomers that have the same connection, but just different 3D orientation. And if you want, I'll put a link towards that video going over constitutional isomers, enantiomers, all that good stuff. So just remember that stereoisomers are going to have same connections, different 3D geometry. And this is exactly what that looks like. So here's an example of a stereoisomer in which we're looking at the cis configuration and the trans configuration. So cis configuration is when they're on the same side. And over here, those methyl groups are pointed up. Both of those methyl groups are pointed up, so when they're in the axial position, which we'll get into what that is. And over here in the trans configuration, they're in the opposing sides. So one of the methyls is pointed up, the other one is pointed down. So this is an example of a stereoisomer because they have the exact same connections, they just differ in that 3D orientation. So now let's talk about cyclohexanes. And this is when we're going to see something called the chair configuration. So I'll do config. So we're going to see something called the chair configuration. Now you might be wondering, well, what is the chair configuration? Well, the chair configuration is a way we can see what our cyclohexane looks like and how those substituents can sort of interact or how they're placed. So the chair conformation is also the conformation in which there's no torsional or angle strain, and all those carbon-carbon bonds are really close to 109 degrees, which is actually where, if we get to 109 degrees, there actually is no torsional, no angle strain, none of that, because that's where our organic molecule is the most stable at 109 degrees. And in our chair configuration, the cyclohexane is actually really close to that. It's about 111 degrees, I believe. So drawing a chair configuration can be challenging at first, but with practice, you'll get it really easily. So one way that I've learned how to draw the chair configuration is, first off, draw two parallel lines over here. So just two parallel lines over here. And now, starting from the farthest line, usually I'll create this long angled line over here. Sometimes I kind of mess up since I'm still trying to learn how to draw it correctly. And over here, this guy will do pretty much the same thing. And now just connect from here. So there's a connection right there. There's a connection right there. And that is a way you can draw your cyclohexane. Like I said, still working on how to draw it perfectly, but this is as close as I've gotten so far, and so forth. So this is what our cyclohexane, the chair configuration, is going to look like. And this guy over here is actually going to be the front of our cyclohexane. So usually what you'll see in most of either your problems or anything like that is this line over here is going to be the thickest. So this one over here is going to be about that thick, and we're going to be moving around here, and this indicates that this is the front carbon or the front side, and over here is just going to be the back side of our cyclohexane. Now there is another conformation, and this is actually called the twist boat conformation. So you can see that this one's the front, that's the back carbon. But here's why this is actually the worst, most unstable or least stable form of cyclohexane to draw out. So over here with these two hydrogens over here, we're going to experience some steric strain. And with these hydrogens over here, just these two over here and these two over here, we're going to experience torsional strain. So I'll just do T strain, and I'm just going to model this as just TS. And this is going to come out to 25 kilojoules per mole of torsional and steric strain, which is not what we want. So with the chair configuration, we have 0, so I'll do 0 kilojoules per mole of strain. So now let's actually get into more depth with this chair configuration, and let's really dive into the different ways in which we can actually make this chair configuration more stable or even less stable. So as you notice with the chair configuration we drew before, we have our hydrogens bonded to each of these corners, each of the corners representing our carbons. Now, they were hydrogens that are pointed up and down, and these are in the axial position. So if you think about like an axis, like the Earth spins around an axis, that axis is pointed straight up or straight down, whichever way you want to look at it. And over here, what we're going to see is a bond over here. So if we see those red lines going up or down, this is going to be a hydrogen bonded in the axial position. Now let's look at our other position, which is known as our equatorial position. And this is going to be going from side to side. Just like the equator is going around the Earth side to side, that's the exact same thing we're going to see with these equatorial positions. So we might have something over here, then down, and this is going to be up, and this is going to be this side and that side. So this is actually how we draw out our hydrogens with this axial and equatorial position. Now, there's this concept known as ring flipping. And ring flipping is, just as the name pretty much says, is that when we flip the ring. So over here, let me actually write ring flip over here. So this is going to be ring flip. So ring flip is when we're going to be taking this carbon up over here and this carbon down over there. So I'll just highlight this carbon yellow and I'll highlight this carbon orange. So this is exactly what we're going to see. So this yellow carbon over here flipped up, this orange carbon flipped up, and as you can notice, our equatorial positions have turned into axial, our axial positions have turned into equatorial. So these hydrogens have basically flipped their positions, and this is exactly what the ring flip is characterized by. When these axial and equatorial positions have flipped, and we see this flip in our carbons. And this is one key fact to know, is that our substituents are going to be more stable in our equatorial position, and we'll get into how that is, and I'll actually show you some examples of what that looks like. But just keep this fact in mind, that our substituents are more likely going to be more stable in that equatorial position. So now let's talk about the 1,3 diaxial interactions. So what is this interaction going to be? Well, this is when we're going to have our substituent, which is going to be on our first carbon, and this is going to repulse between the hydrogen on the third carbon and the fifth carbon. So if we number this out, this is going to be 1, 2, 3, 4, 5. So this is our fifth carbon. This is our third carbon. There's going to be hydrogen over here, hydrogen over here. Let's say for this example, our substituent is CH3, and there's going to be a repulsive force experienced between the hydrogen on carbon 5 and the hydrogen on carbon 3, which is exactly what our diaxial 1 to 3 diaxial interaction is. We have two of these carbons, or two of these hydrogens. One is on the third carbon, one is on the fifth carbon, and these are in axial position, and they're feeling a repulsive force from the substituent on the first carbon, which is usually going to be, well, for this example, we have methyl. Now, if we ring flip though, this carbon is going to move down here. So our CH3 is going to be right here. CH3, our methyl is going to be right there. So this was our first carbon, and we just number it off. 2, 3, 4, 5, and I'll go all the way to 6 for this one. So 6, this carbon flipped over here, and now the hydrogens will be moved over here. So it'll still be in their same carbon position, but this hydrogen is going to be over here on that 3rd carbon. This one's going to be on the 5th carbon. And as you can see, those hydrogens are pretty far away from the methyl, so there's none of that repulsive force, and this is exactly what we mean by having that substituent in the equatorial position, because there's no repulsive force anymore compared to this chair configuration over here when we ring flipped it. So I'll just do ring flip, just to acknowledge that that was a ring flip. So when we ring flipped it, now we have our substituent on the equatorial position, and now everybody's happy. So now let's go through some practice on, ring flipping and looking at these diaxial interactions. And we're going to start off by looking at 1,2-dimethyl. So dimethyl cyclohexane. And again, sorry for the bad handwriting, but first let's look at what we're looking at. So dimethyl, this should be a Y. So dimethyl cyclohexane. We have 2 methyl groups. So these are going to be in the 1st carbon, 2nd carbon. So you have CH3, CH3, and over here we have an H and H. So just for simplicity, I'm only writing out the hydrogens that actually interact with our substituent, our methyl group over here. So we are going to feel a diaxial interaction over here and over here. Remember, diaxial interactions can be usually with the substituent and a hydrogen. It will be labeled, but for this example, we specifically have 2 of these CH3H diaxial interaction. So we have 2 of these, and this is going to result in an energy of 7.6 kilojoules per mole. Now we also have an interaction between these 2 methyl groups. It's not to the point where it's an eclipse interaction, but this is going to be a gauche interaction, gauche conformation. So if we write that down, we're going to have 3.8 kilojoules per, I need to rewrite that, kilojoules per mole. So the total strain for this configuration over here, and these 2 are going to be our cis configuration. So this is the cis configuration of a 1,2-dimethyl cyclohexane. This is going to end up being a total of 11.4 kilojoules per mole for this guy over here. Now, when we ring flip, we're only ring flipping so then we can find the most stable configuration of our organic molecule that we're looking at. But over here, if we ring flip it, we have the CH3 down here. Then we have our CH3 is going to be right here. So CH3. Then we're going to have our hydrogen right here. And we're going to have a hydrogen over here. Now, I didn't write that hydrogen over here on that 4 carbon just for simplicity, but we did flip. So we ring flipped and this carbon moved up over here. So I just wrote that hydrogen that's there. And like I said, I'm just writing the hydrogens that interact with our methyl groups just for simplicity. And over here, we're going to have an interaction between our hydrogen over here and the methyl, creating a diaxial interaction. Same thing over here with this hydrogen over here. And over here, these methyl groups are still going to interact with that gauche conformation, and this is going to result with the exact same energy, kilojoules per mole. So 11.4 kilojoules per mole, because we have 2 of these diaxial interactions, and we have this gauche interaction over here between that methyl over here on the top and the methyl on the 1st carbon. So for this one, our methyl groups are still on the 1st carbon and 2nd carbon, but now it depends on which part of the side that we put it on. So over here, we could put the methyl on the equatorial side over here, and this one as well. So, but this equatorial side is pointed up. This one is pointed down. And that's how we create our trans configuration. So, all right, trans over here as well when we ring flip. So we only have this gauche interaction or gauche conformation, and this is only going to be 3.8 kilojoules per mole. And that is actually the lowest energy form that we've seen in any of these organic molecules. And let's see if we ring flip it. If we ring flip it, let's see if that results in a lower energy form. So this CH3 is going to move down over here. So CH3 is going to be over here, CH3, and the methyl over here is now up. But as you can see, we have a hydrogen right here, a hydrogen right here. Then down here we have a hydrogen, and we feel a repulsive force between this hydrogen and the methyl, this one as well. So we basically have 4 diaxial interactions. Now, the reason why that we know these 2 hydrogens are interacting with this methyl over here is because these are on the front side of our molecule, and these are the hydrogens that are in that, now it is the axial position, which they're going to feel that repulsive force since they're both on the axial position in the front of our organic molecule. So we're going to have 4 of those methyl hydrogen diaxial interactions, and this is going to result in 15.2 kilojoules per mole of energy. So just to summarize these diaxial interactions, remember, these diaxial interactions only occur if our substituent and our hydrogens are both in the same position. For example, we're going to see this diaxial interaction occur because we have both of this hydrogen and this methyl both on the axial position. So they are going to interact, creating those diaxial interactions. Over here, with this methyl, same exact thing. They are having a diaxial interaction because they are both on that axial position. Now, in this gauche over here, both the methyl and both methyls were on the equatorial position, so they're going to feel that interaction. But they will not feel any interactions with this hydrogen over here or any hydrogen that's in its axial position. And over here just gets too far away, especially since this is the front of the organic molecule. This is the back, so that's why we're not going to have like this hydrogen interact with this CH3 over here.